So, how do you pronounce Yon? Is that Yonsei University?
Yonsei. Yeah,
Yonsei.
Yonsei University.
It's a very good university. I had many good friends when I was at
Oh,
Harvard. I had a few friends. Suryan was my friend back then. A very good lady, excellent researcher, and then she came from that university.
I
And
see.
uh, I had many friends from Korea, and many
Yeah,
amazing researchers, and then very nice people. We were close family friends too.
I see.
Yeah.
Good, good.
Okay, we are live.
Sounds good.
All right. So, good morning, everyone. Welcome back to our e-seminar series on Translational Biomedical Engineering. Today, we are very pleased to host Dr. Soo Kim, the Director of Additive Manufacturing Laboratory, and also the Acting Director and Associate Professor of School of Mechatronic Systems Engineering at Simon Fraser University. So Dr. Kim is from the west coast of Canada, Vancouver, which is less colder than the eastern part of Canada. So before we start, I have a few housekeeping notes. During the talk, if you have any questions, please ask them in the ask a question box. This way we can keep track of questions. If you write the questions in the chat box, we may miss your question. So make sure that you write them in the ask a question box. Also, as usual, we would like to hear your feedback about these e-seminar series. So please participate in the polls. There's a poll section box down there, down the basically the platform that you can participate and share your thoughts with us. So as you may aware of, we have a line of speakers for the spring. So after Dr. Kim's talk, we have Dr. Hodge from Revolution, Hodge Henny. He will talk about their non-invasive technology for measurement of mechanical properties of hydrogels, and we're looking forward to his talk. Also, as always, if you have any comments, any feedback, or anything that you want to share with the organizers of these events, please feel free to email me and Human. Our emails are available in this slide. Also, if you want to receive the most up-to-date information about this series, please follow us on Twitter, LBME. And also, we also have a YouTube channel that you can watch the videos from the previous speakers. Also, last but not least, I would like to thank our sponsor, Montreal Transmed Tech, who has been with us since since the beginning of this e-seminar series. Thank you, Montreal Transmed Tech, for the continuous support. So with that, I would like to invite Dr. Soo Kim. Dr. Soo Kim is an associate professor of the School of Mechatronic Systems Engineering at Simon Fraser University. He is also the acting director of the program. He was selected in 2007 as a Brain Pool Fellow for his sabbatical at Seoul National University in Korea, and visited Swiss Federal Laboratories for Material Science and Testing at ETH. Prior to joining Simon Fraser University, he was a senior research scientist in Xerox Corporation for 2 years. After he finished his postdoctoral research associate at MIT, where he spent 2.5 years. He received his bachelor's degree from Yonsei University in 2001, a master's and subsequently a PhD degree from Korea Advanced Institute of Science and Technology. He was the winner of the Quadrant Award in 2007, International PhD, for which is a competition for international PhD thesis. Also, he received Hanwha Corporation's New Faculty Award in 2016. His research interest is broad and is in the field of advanced 3D printing for energy and sensing applications. Thank you very much, Dr. Kim, for inviting our talk. I'm quite familiar with your research. It's very interesting to me and very high tech. So Dr. Kim is going to talk about 3D printed wearables and biomedical sensing robot systems. So without further ado, I would like to invite Dr. Kim to start his talk. So the virtual floor is now yours.
Thank you, Mosen, for kind introduction. Can you hear or can you see my presentation now?
We can see your presentation and your sound is great.
Perfect. Thank you for having me here today. Actually, Mosen and Human splendid jobs so far in the translation biomedical the e seminar series. I'm so happy to be part of this series. Although, as you may guess from my introduction, my research field is applied science. As you understand, the translational research is specifically designed to improve health outcomes, right? So there are some mixture in terms of outcome between the applied science and the translational research in my research. So I hope that you enjoy my talk today regarding the 3D printing and wearables and sensing robots. So before moving into research part, I like to introduce Simon Fraser University. We have 800 pounds gorilla in Vancouver, as you know. UBC is there, right? But SFU is well known nowadays in terms of uh, freshly growing university with a focus of the research, and we have some impact on sustainable cities and communities and biomedical engineering, so stuff like that in the Metro Vancouver. So SFU is well known for that location. We are located on top of the mountain, and the engineering, especially sustainable engineering and mechatronics engineering, we uh, relocated from that top of the mountain to the downside of the mountain, about 25 kilometers away from that campus. And as you can see here, the two main buildings are located in Surrey. So we built a new engineering building which has a sustainable and smart city concept. We have a lot of trees inside a building like this, right? So we are locating mechatronics department. My department is located inside of this building. On the third floor, we have a mechatronics kind of research center, and all the fields like biomedical mechatronics and advanced manufacturing mechatronics and some control systems, all those labs relocate to this new building. So if you have a chance later, visit Vancouver, don't forget to come to SFU, please. All right, let's move on to outline of the talk. So today's talk, I'd like to introduce you why we need 3D printing to get the unique form factor of devices. And I want to emphasize about the usefulness of 3D printing to fabricate and manufacture wearables. And basically two parts of the talk today. The first part is about the wearables. Main topic will be wearables. But the second part, I want to give more weight to second part, which is generated in my lab, the concept of sensing robot. So there was a field, has been a field like robot sensing, of course. But we created this terminology as a sensing robot because we want to have some interaction between human and robot by having this sensing capability to the robot, right? So 3D printed sensing robot, I want to explain and demonstrate some research outcome we have done about these sensing robots. And in order to get that, so there's a concept we call the architecture solid. So if you think about the solid, can we give some design aspect? Can we design some mechanical property? Can we design that with some periodic structures inside, right? That concept is about architecture solid. So by using 3D printed architecture solid, we realized robot body, some mechanically tunable robot body, as well as a sensing feature too. So that's why I want to introduce that concept. Moving on. All right, so first part is about let's think about sensor. Let's think about integration of sensor first. So before going into sensor, when you think about the cognitive systems of human body, so these chart, I mean the schematics gives an idea how our decision making is going on. From the outside environment, a lot of environmental information comes to our sensors. What are sensors for human body, right? So eyes, nose, tongues, those kind of things. We can get the information by perceiving and then understand that information, and eventually we can decide our decision. This is conventional, our cognitive system. In this kind of cognitive system, uh, um, important part I'm focusing on is about getting the information. So when you think about the Internet of Things and the connected world, that kind of concept, important feature, important device is about sensor. So by replacing our sensors like eye, nose, tongue, can you get those by right the devices? So yeah, Internet of Things and wearables, sensor can do perceive this information well. But as you know, sensors historically was rigid, right? All different forms of sensors, there's a mismatch, possibly mechanically mismatch between the wearing our human body or the sensors. So there's a huge need to get some curvilinear form factor devices, which means flexible or stretchable or three-dimensionally integrated, right? We call this structurally integrated sensors and interconnections. So there were several demonstrations recently regarding the wearable sensors, can be wrist type or can be printed directly on the skin, or sensors can be structurally integrated on the tip of a robot, something like that. So in order to realize this kind of curvilinear form factor devices, definitely we need some flexible manufacturing methodology. That's why we focus on 3D printing, and we need fabrication methodology for 3D unique form factors, right? So moving on to the introduction of my lab. So yeah, that's the discussion about 3D printing. That's why my lab is focused on 3D printing, and this slide is quite busy, but the left side is a kind of fundamental technology you are looking at. So we're developing 3D printable novel materials, which is especially with the conductive materials. Without printed conductive materials, we cannot realize any sensors or any electronics, right? So that's one of the important part. And then we are interested in developing new technologies in terms of a 3D printing process, something like a cold shell nozzle-based 3D printing or six-axis robot-based 3D printing, stuff like that. And also, important thing is about topology optimization and the thermal or electrical simulation for your 3D printed objects, right? So these are kind of fundamental. And when you see the right side, those are the application by using 3D printing. You are interested in focus on electronics. So 3D printing can make individual sensors as well as interconnection. This is important thing. We initially focus on devices. When I started my lab, we were very interested in making physical sensors, chemical sensors, stuff like that. But recently we realized that one of the important feature of this field is getting connected of those individual devices, individual components. So I'm more interested in interconnections than sensor itself nowadays anyway. So that's 3D printed electronics. And second part is 3D architecture solid, as I mentioned. Mechanical components need tunability, tuning capability of mechanical property. So we can design solid by having periodic structures, whether it can be flexible or different rigidity or compressible. We can give solid with some architecture. That's why we call the 3D architecture solid. So this field is nowadays growing too. This is good for biomedical robots body design. So this is one big field in my lab. And the third is a 3D sensor, which is in some sense that belongs to the 3D printed electronics, but we want to focus more on sensor part by having, again, 3D printed devices. As you can see here, some 3D object which can embed all the conductive devices inside of 3D object together. Then we can let's say, utilize the spaces on top of device. Usually when you think about sensors, it's just deposited on the surface of, right, two-dimensional surface. Then we cannot use 3D dimension on top of that surface, right? So our concept is we want to utilize stacking up devices together inside of 3D space to utilize all 3D available spaces, right? So that's our concept. All right, so moving on, then let's think about 3D printable structure electronics. So I discussed that 3D electronics, which is structurally embedded. And there have been a lot of research done about this field in terms of device fabrication, like miniaturized capacitor, inductor, stuff like that. And then by having the architecture solid, energy storage device has been splendidly increased the research nowadays, and also wireless transmitting devices in terms of data communication, 3D printed, and all those sensors and robotic applications with the sensors too. So my talk today is specifically focused on biomedical wearables and robots, sensing robot, sorry, applications developed in my lab. I'm not going to go over all those, right? So maybe the talk is more on the biomedical sectors today. Okay, so before moving on to introduce to you our outcome in terms of wearables, I want to say about the first number one important thing in my lab, which is actually interface with the biomedical wearables or sensing robot. That's conductor, right? So 3D printed conductor. Without careful consideration of this conductor, it's not going to be useful for wearables, right? Because it's going to be contact directly to our skin, or it's going to be uh, fabricated on the robot hand, and then it's going to be contact with the human body. So without careful consideration of conductor, we cannot realize reliable device as well as safe device, right? So we have been working with main conductors are like metal nanostructures, like silver nanoparticles, silver nanowires, and also graphene. Those. The reason we chose those because there are a bunch of different conductors in the market, but important thing is conductivity. So if it is not reaching to like over 10 to the 4 Zeeman per centimeter, which is Zeeman per centimeter, not the Zeeman per meter, right? So if it's not reliable above this level of conductivity, it's not going to be useful. I mean, we can get the resistive sensor with, let's say, 10 Zeeman per centimeter level carbon nanotube or something too, right? But um, I like to have more reliable and conductive feature than the resistive sensing. So that's why initially we started with the silver nanoparticle, which is like this processing. Whatever methodology of printing, we can print it. And then that nanoparticle-based pattern needs to be sintered to make patch type conductor, which can generate the load for the electrons, right? So this kind of process can be applicable any kinds of printed electronics, but main thing is we want to make it 3D printable. That's why we made somewhat thixotropic, or I can say viscose feature with some silver paste or the copper paste using these silver nanoparticles. That's a main material for our conductor nowadays. We have different sort of printable conductors like a metal filament or composite filament with carbon fiber, those kind of things. But the main materials we are relying on for the biomedical application nowadays is the silver nanoparticle based silver paste. Right? So keep that in mind, please. And again, as I mentioned, we are very interested in making the interconnection of all those connection to chip, right? Instead of having just to focus on making a really reliable device. Of course, device fabrication is important. Highly functional component like inductor, capacitor. I'm going to show you those later. Those are basic component for biomedical sensors. Those are very important to be 3D printable. But another thing is we want to make less connection with external wires, external flying wires, right? So instead of having those, we want to make all interconnected by 3D printing. That's our concept. All right. So first thing is this slide very busy, will be very busy, but I want to introduce to you what we've done in terms of wearables. So the first part is we are interested in the accelerator. So we call the single axis accelerator. We have a bottom electrode and top electrode, then we have a capacitor, right? So when the top electrode can be vibrate very sensitively, then it can catch any types of acceleration. So we we can design that top electrode as a membrane type or serpentine type. Then we can make a very sensitive accelerometer, sorry. So that can detect any kinds of the motion, and even that accelerometer is attached to our body, it can detect the heartbeats. So if you can see this graph, we attach this accelerometer on our neck, pulsing zone, right? Or the elbow inside here, pulsing zone, and then we can get very reliable heartbeats sensing, which is similar to PPG. I think you are familiar with the oximeter-based PPG, right? So this is identical signals of heartbeats. And then we are interested in the blood pressure measurement, actually. There's some methodology to estimate the blood pressure by having ECG and the heartbeats together. I didn't post it here about the processing here, but we can get this kind of, this is accelerometer on our pulsing zone on our wrist here, and ECG sensor, which is attached close to our heart. So we have a paired sensors together. So one is accelerometer, and another is just electrode, which is stretchable. That's why it can be conformally contact to our skin. By having this a paired system, we can get the blood pressure measurement. So that is estimated, and then that blue curve is basically detected by the user cuff wrapping method, right, as a reference. So, and then these straight lines means my student is moving to pump hearts more, right? So right after moving, the blood pressure is jumping like that, jumping, right? I'm sorry, this is the background of the Excel. I believe the straight line is missing, but that is around here and here and here and here and here. So right after motion, our blood pressure is jumping, and that trends can be detected. Although there's some discrepancy between the cuff wrapping method and the estimated method, but we have this kind of trend of up and down of blood pressure, which is not absolute value, of course, but we can ambulatory measurement is possible by wearing these. So we demonstrate this about 5-6 years ago, and then we are interested in moving on to make a smaller scale of wearables, but my interest is moving from this kind of physical sensing to chemical sensing. So I'm going to go over that again. So next interesting wearable or portable system we develop is portable sweat sensor. We are much more interested in the physiological sensing of our chemicals inside our body by having the sweat sensing, right? So in that sense, we made printed sensors, enzyme-based sensors, and all those potential state and the interconnections are 3D printed too. So we demonstrated sweat sensing feature, but the good thing and bad thing is at back then the silver, this is all silver-based electrode. We realized that the combination of enzyme and the silver was not that perfect because of the silver's kind of reactivity. So we just dumped the methodology with enzyme-based chemical sensing. We would like to use chemical sensing in terms of ion sensing with the ion selective membrane. So we turn our gear into the ion selective membrane based sensor. So this is kind of a sensing platform. We developed the portable digital microfluidic, which can vertically moving on, and then we can get the droplet sensing and droplet mixing, stuffs like that. So like if you can see this vertical tower, droplet is moving on from the bottom to top. So this is electrically moving droplet against gravity. So by having this platform, we can select some heavy ions and lighter ions, and we can detect the targeted ion. So we utilize this digital microfluidic sensor. So these are about 3D printed wearables and the portable sensor system we developed so far. And especially about that ion selective chemical sensing and neuromorphic, we interested in sensing our saliva. So we want to make kind of artificial saliva sensor like our tongue. That was our kind of objective. So we made a different platform of study. This is kind of well-known field we call the ion selective membrane-based thin film transistor system. So as you can see, yellow is electrode, so source, drain, and gate, and we extend the gate, and then that gate is modified with ion selective membrane, and when the ions are selectively transmit, then the gate electrode resistance can be changed. By having this mechanism, we can get the transistor, right, the signal. So when this ion selective membrane is targeted with ammonium ion, then we can get the very linear relation we can get. So back then, we are interested in more on this sensor itself. But again, as I mentioned, we are interested in making sensory system. That's why we thought about one of my PhD students is focusing on neuromorphic. So as you can see, neuromorphic is kind of sensing system in our body. We want to see not just the sensing, but the processing of that signal, right? So we have kind of mimicking, right, our neuron. So the stimuli is coming into the sensor. This is the same thing like this ion selective membrane. And then that signal can be activated by electrical oscillator. So we designed the 3D printed electrical oscillator, which contains all the component inside, like resistor, the capacitor and inductor, and then resistor outside. So we design the oscillator. Then oscillator can give the AC signal to synaptic transistor. Then we can get the potentiation like, right, behavior. And then eventually this synaptic transistor has mechanism to have a memory effect. With a smaller quantity of ions, we can detect some um, um, some signals by training. That's a beauty of neuromorphic system. So we developed this system to realize from sensor act activation and then eventually memory effect too as a neuromorphic system, right? So this kind of approach is moving on for the chemical sensing. All right. So when we talk about this sensing, what time is it? Oh, 34. Okay. When we talk about these wireless, the sensing signals, we are interested in transmitting wirelessly. So by relying on those expensive silicon chips, we can get the different wireless signals from like a Zigbee or Wi-Fi, those kind of thing. But we would like to make a simple and cost-efficient mechanisms, right? Which is well known as LC circuit. L is inductor and C is capacitor. So by having this LC as a pair, we can get the electrical the resonance that generate interesting resonant frequency, and that resonant frequency can be shifting if the dimension of this LC can be changed. So we designed the LC initially like this, and then if this is attached to human body and if there's any strain happen, then this LC circuit's dimension is changed. Then original resonant frequency, which is a red one, can shift with a certain stretch strain. So by having tensile strain, we can detect resonant frequency change like that. So that was the mechanism we developed. So LC's resonant frequency itself can be shifted. Then by reversing it, we can get the how much strain is applied to human body, right? So that was the strain sensing mechanism. And another mechanism we developed is these resonant frequencies, I mean, the peaks quality factor change. These resonant frequency quality can be significantly rely on the resistance of circuit. So for example, we have a loop of this LC connected with ion selective membrane. Then if we have a targeted ion through this ion selective membrane, then resistance of whole loop of this circuit can be reduced. When we have a reduced resistance, then we can get the quality factor, or the peak can be increased. So by detecting specific ions of your saliva, you can get the resonant frequency quality factor can be increased. So that was the methodology we developed. So these two mechanisms are main thing. One is resonant frequency shift, or another is quality factor change. So we were using these a lot for the sensing applications. All right. Then yeah, that was published last year with wireless chemical sense. That was kind of first to try without any expensive silicon chips or something, right? All right. So let's change our gear toward to sensing robot. So this I like these schematics a lot. So interaction between robot and human. So as you can guess, our era will be moving on to AI or robots, those kind of thing, right? So some part of our populations, like seniors or some children's, um, it's not easy to educate them to wear wearables. That was the initiative or initial motivation for me to move my research from wearables to sensing robot, right? So instead of having wearables on our body, why not having periodic interaction with robot and the human, and then giving our biomedical signals to robot? So I cannot say this sensing robot can replace the technology of wearables, because there are sectors of wearables which can be continuous monitoring, or let's say ambulatory monitoring. In that sense, robot cannot touch with you for a long time, right? So it's not going to be replacing, but there's a somewhat complementary approach of sensing robot for the some part of the wearables, right? So that's our niche field we want to focus. So when you think about humans' hands, focus on hands capability, we can do have gestures, visions, or the touch, right? But chemical sensing is not available with your hands, right? You need to use your nose or your tongue. But when you use your robot, I mean, if you have a chemical sensors on the tip of your robot hands, you can do have a chemical sensing. You can do have a biopotential sensing, something like ECG or EEG or EMG, those kind of thing. You cannot measure your electrical signal of your hearts by your hands, right? But the robot can do. That's our concept of the sensing robot. All right. So this is a fresh paper we published recently regarding this sensing robot, 3D printed sensing robot. Basically, why we need 3D printing? Because robot, you cannot replace your robot, let's say every month or a weekly base, right? So you once you have your robot can go with you for a long time, like a few years or something. But robot hands can be replaced whenever it is contaminated or whenever the function is not working properly, something like that. 3D printing is the key technology we can apply because it's customization of the functions and device is good fit with the 3D design and the 3D printing, right? So this concept is based on human-robot interaction. Once again, it's complementary technology with the wearables, and the medical cooperative robots can be available, and also social assistance service is possible with the robot. Robot is not just hardware. By having AI or machine learning inside, right, then it can be a very smart and intelligent feature instead of having just sensory thing, right? So there are a lot of features there. So combination of AI and this sensing capability, we can have a lot of interesting things can be done. Right. So moving on to sensors capability in the sensing robot, we very much interested in the body itself first, robot body itself. So we done a lot of 3D architecture solid research in my lab. So starting from around 2015-16, we initially start with the rigid format of periodic structure. What are well-known rigid structure, which can be the main body of sensing robot, right? So this is a rigid octet structure. We are interested in 3D printing of different materials for realizing mechanical tunability. And rigid octet and double gyroid structures were studied too, because these are very good for increasing surface area for energy systems for robots, etc. Right? And then we are interested in more mechanically metamaterial, which is showing different, right, mechanical properties than conventional mechanical structures like oxalic, which shows a negative Poisson ratio. I'm not going to go details about that here, but if you are interested in just to follow our papers in my website. And recently, we are interested in mechanical metamaterial like origami, which has some durability when it is bent or when it is compressed. An interesting thing about the origami is if we the embed capacitors inside of like this, when it is squeezed and compressed, of course, this capacitor gap can be shorten or the reduce, right? Then capacitance detection is easy. So this kind of origami sensor was used. So nowadays we are interested in sensing feature with this kind of origami structure and the more on the robot body with this kind of rigid structures, right? So first robot we want to demonstrate you is we call the cooperative sensing robot with a touch sensing feature. So as we discussed in previous page, robot body is composed of periodic octet structure, and we embed at the tip of robot finger with a capacitive sensor, and then we design inside of these gap dielectrics, right, to get a sensitivity higher. And then joint is important. J is joint. Joint can be banded like that. So we need to have a durable feature inside of this joint with the oxalic structure we embedded there. And then that can be applicable to kind of robotic gripper like this. And then the sensing feature can be, if it is touched with, sorry, this is white block is a kind of insulator. When insulator is touched, we programmed it, it's not moving. But when we touch with a capacitor like a human body, right, and then capacitance change is higher, then robot finger is moved, so or bent. So we have the smart feature here. So if you can see here, so touch with the insulator, capacitance change is small, then this finger is not moving or bending. But when touch with the human, right, and then capacitance change is high, then it's bending like that. So we have some smart feature there, and with this capacitive pressure sensor can detect whether the object is big or small, then we can give some different programmed force to grab something, right? So something like this, right? And then it's gonna be gripping like that, right? So yeah, that was our first robot, which is pressure detectable, touch detectable sensing robot. And then second sensing robot we are interested in more is about the chemical sensing, as I mentioned, right? So when we designed the fingertip, so this is the left side is finger design and the right side is actual sample. Uh, the top front of the finger is ion selective membrane based chemical sensor. The back side, like our nail side, is with LC circuit, which can deliver wirelessly signal, right? So we have uh, I mean, interconnection from front to the back side through the conductive 3D printing inside. So this is quite well organized device. And then this can reduce, I mean, when the ions are detected on the ion selective membrane, then the resistance of this closed loop circuit is changed. Resistance change can give you the idea how to program the motion of the finger. So we have designed this kind of robot hand, and then when the resistance change while wired situation, it can move right the finger. Then visually, people can see how much concentration of ions are there. For example, 0.01 mole potassium ion movement is a bit small, but by increasing that concentration, that finger motion is significant. Then seniors or someone who cannot move, they can see a robot's finger motion visually to see the concentration, something like that, right? So this video shows you 0.01 mole. It's very spontaneous sensing, like this small movement, but by increasing concentration of ion, it's going to be moving more, and zero point 0.5 mole, it's moving much more, and then eventually 1 mole, then it's going to be standing like that, right? So that can gives you the idea how chemical sensing is happen. Right, moving on to 3D origami, one of the architecture solid we introduced. So there are a bunch of different origami research, but we are interested in one specific 3D origami, which shows quite compressive features. So third cooperative sensing robot for the biomedical sensing signal, we developed this origami, we call the Miura Ori module, which is well known, but we tuned the design to make durable feature for your finger doesn't need to be bending the other side, right? It must be bending only this side. So we have some tuning of mechanical structures with a larger structure of Miura Ori inside, and then the smaller structure outside, and then angle was designed, then it's going to be moving only this way, not the backward, right? So this is bending feature of this structure. By having this origami structure, we have this kind of hand design, and at the tip of this robot hand, we have electrodes. Those electrodes, mainly 3 electrodes are needed for your EMG or ECG measurement. So this is the demonstration of that hand, right? And then our muscle, electrical signal of muscles can be detected with these robot hands, something like that. So now this is kind of preliminary demonstration with 6-axis robot and our sensing robot hand, but it can be implemented into humanoid robot eventually to measure this kind of electrical signal. And yeah, and this origami is very interesting in terms of sensing once again. So it has some durability, and the electrical capacitance measurement is quite sensitive by having pressure on top of something like a smart insole, right? This capacitor gap can be reduced significantly like that. Then we can have a capacitance signal on the whole, I mean the entire our foot, right? Then eventually we can get this is 3D printing process. Electrode is embedded inside of insole and then eventually made like that. And then capacitance, the change is quite linear, so we can get the reliable capacitance signal, and then we can get the mapping of it. So when we have some issue with our foot, like a plantar facilities, then the pressure is usually applied on the back side of our foot. But when the posture is corrected and then these plantar facilities is changed, then we have some reliable pressure application through the our foot like this, right? So we can detect this kind of thing whether the patient or the participant has a plantar facilities or not by having this kind of mapping, right? So this is done by 3D printed origami inside. So origami itself is the structural unit inside of smart insole as well as a sensing component, right? So that's the beauty of the 3D printed sensors inside of this. Right. And then during this COVID last year, I think you heard about some uses about the engineers' contribution to having a joint force together with medical doctors and etc. I did my best during the lockdown of my lab too. So we thought about the significance of COVID-19 pandemic situation. And as you know, a lot of patients initially, not now. We realize nowadays not many patients needs actual ventilator, but back then, like May 2020, last year or around summer, we thought a lot about generation of cost-efficient ventilators. So our thought is like this. One of the important cheap version of mechanical ventilator is like this AmbuBag, automated AmbuBag. But when you think about AmbuBag can be replaced much because of the continuous stress and strain generation. Can we generate this kind of strain periodically like this instead of having shock like that, right? That's our own idea. So by replacing these conventional AmbuBag, we want to make origami back, right? So this is the eventual prototype we generated. So basically this origami doesn't need to be big like this because the volume can be hugely changed. Compression and release, 85% is changed. And then the strain generation is periodic like that, essentially because that's based on individual joints, right? So compare with this AmbuBag, it's going to be much mechanically durable, and we can tune these air volume depending on customization is possible depending on patients. So reliable air delivery about 300 milliliter or about 600 milliliter is possible. And this is the video for you to understand about this origami bag based mechanical ventilator we developed. So this is now pending invention disclosure, and the manuscript is in review now. So yeah, this is our work related with the architecture of the solid during this pandemic. All right, so I think I almost done my talk. So I want to wrap up with the introduction of our recent efforts in the sensing robot. So demonstration with our British Columbia engineers community with the innovation magazine of cover front was done with our sensing robot, pressure sensing robot, and the chemical sensing robot. We call the title as a soft yet durable robot. And then three different genre covers with the pressure sensing robot and the chemical sensing robot. The conceptually we can go to space with this chemical sensor, and then it can be doing chemical sensing on the, for example, soil, right? The Mars soil on behalf of a human body, something like that. And the recent one, actually this is not released yet, but it is selected March 5th, 2021, March 5th genre cover with our concept of sensing robot, right? So hopefully you understand about every concept I deliver about the sensing robot. So I'm looking at the future, right? So we're focusing our lab much more nowadays, making 3D printed sensing robot features. One day, sorry, someday, AI equipped sensing robot may be possible to prescribe medications for you instead of. So whenever you visit your family doctor with some cold and just general symptoms, do we need to meet medical doctor? That's the concept, right? Maybe there's in future we have some um, walk-in clinic only equipped with AI-based sensing robot, and these sensing robot detect your temperature or your coughing or any electrical signal like heartbeats and etc. And then that's based on huge amount of database. AI robot can give you the prescription. Why not? Right? So that's the future I'm looking at. All right. I really like to thank my students and funding agencies. So I want to have this slide, of course. Of course, thank you for your attention. But I want to have this kind of scenario once again, right? But this is 2019 summer. I miss this kind of, right? We can meet together in the restaurant nowadays. But whenever I see this picture, um, I like to go back, right? So I want to show you my grooves, kind of good timing past. Thank you so much for your attention once again. So any questions? I will take your question from now.
Thank you so much, Professor Kim, for your great talk. It's a bit so. The question probably is that can robots distinct human being in the future? You know, like so. I mean, they can replace us, and then it's a bit scary. Anyway, so yeah, before we go to Q&A, we got several questions from audience. I would like to also, you know, you have some moments to breathe, and then I'll go through some advertisement for our future talk,
Of
and,
course.
and then
Go ahead.
we get back to Q&A.
Sounds good.
So yeah, so as you know, we have a great line of speakers for our winter seminar series. So please follow us, and for the upcoming seminars. Next week we have Dr. Anis Hajheni from Revolution Company that he's going to talk about the new device or instrument that they develop for measuring the rheological properties of the biomaterials, hydrogens, and other materials non-invasively. And to get the updated seminar series information, just follow us on Twitter. And then if you have any question or comments, you can send us the email. And I would like to also thank Montreal Transmit Tech for giving us this opportunity to have these seminars up and running. And by that, I would also I would like to ask the audience to ask their question in the Q&A box. and we share the question with Professor Kim. Okay, let's go to Q&A box. So the first question is from one of our audience about the silver and the biocompatibility properties of the silver, and if this silver is biocompatible, is it stable, and how you stabilize the silver, and for how long it can be continuously. I mean, the silver can measure continuously in real time before oxidation.
Sounds good. Thank you so much for that question. That's one of our our lab's main issue for a long time. But be mindful that we're not using silver nanoparticle at the end. So silver nanoparticle has high reactivity, no doubt. But once it is cured and then made as a silver patch, we can say, a conductive patch, the reactivity significantly reduced. And then once it became a conductor, so we cannot guarantee 100% of silver nanoparticle comes to conductor, right? But over, I believe, 99.999% of silver nanoparticles convert into the silver patch. Then once it became conductive patch, it's quite reliable during few years. We check even 2014-15 version of silver sample. Nowadays, it's conductive and it's working. Yeah, so no doubt silver nanoparticle is reactive, but again, electrically converted, then it's okay.
Thank you so much. So another audience, Koshia, has a question about, if you can elaborate a little bit more on why you're using auxetic structure in the joints in the robot system that you've shown us.
Great. Thank you so much for that question. So we are interested in making durable joint. That's initial start, right? So when you think about the auxetic is volumeric expansion, volumeric contraction, which means if we have a normal material, one side expansion, then another side must be contract, which is positive Poisson's ratio, right? But auxetic shows one side is expand, the other side is, the vertically, slightly expand again, which is negative Poisson's ratio, right? So with that kind of feature, we can get 3D structure, which is volumerically expand or volumerically contract. So when we have joint with this kind of auxetic structure, then when it is bent during the contraction one side, the other side is contract too. So basically, if it is expand, it's going to expand together, all together, or contract together. So we can capture some mechanical durability using this. So it's ongoing topic. We are explaining that by having the experiment. So, but we initially thought about mechanical durability. How can we get the mechanical durability of moving joint to get the volumeric shrinkage together? That's why we use the auxetic structure.
Great.
Thank you.
Mahdi is asking, are you using or planning to use any biocompatible biopolymers in your sensor or in your robots?
That's a good question. Yes. So as you can see, this is kind of the stage of a conceptualization of sensing robots. So we don't have any biomedical features actually. So we have conductive feature as a sensor and the robot body with the mechanically tunable, something like that. But in future, next stage is having more biomedical features on the sensing robot. So in that stage, of course, we need some biomedical, right? The polymers and etc. So yes, the answer to your question is yes. I'm considering that too. Yes.
Great. Looking forward to see the outcome later. So
thank you.
another question about the chemical sensor is that because it was really nice, moving the finger up to, vertical position. One of our audience is asking, if 1 molar concentration is very high, which application needs such a high concentration?
Well, this is what we demonstrate. We want to show concentration discrepancy from 0.01 mole to 1 mole. Actually, some exaggerate the situation, right? So maybe 1 mole is not going to be useful for any application, as you mentioned. But yeah, the sensing window is important. So we can say, depending on our programming, we want to show with a resistance change really small, like a point zero zero 0.001 mole can be moving too. So it depends on program, but we want to demonstrate some exaggerated scenario of the demonstration.
Thank you so much. I see Mohsen has lots of questions, and I also encourage others to ask their question in Q&A box. So Mohsen, that's your turn. Please go ahead.
Well, thank you very much, Dr. Kim, for your very
Sure.
nice presentation, and Human for, I've been seeing the questions, the many questions that I have in my eyes. I mean, he knows from my face that I'm just jumping up and down and then waiting for the time to ask questions. So I'll start with one question, or maybe I'll start with the first question because there are other questions in the Q&A box that I would like to let the audience also have a chance to ask their questions before I ask mine. But my question. So first of all, it's a very interesting concept, having this sensing robots, and I can imagine that in the future these robots can be used in environments that humans cannot go. Maybe after disasters, in disaster conditions, when it's not possible for human to go to certain places, maybe in battlefields, maybe in extremely harsh environments that is not suitable for human to go. Maybe and then one good example is the space. So my question is actually around that type of application. So when you go into the areas that you have like harsh environments, you're dealing with extremely high or extremely low temperatures. You're dealing with the presence of contaminants in the environment, or relatively low humidities or high humidities. So these are like areas that are not good for human. They're not environments for human to go. So do you have any comments about the environmental impacts, such as temperature and humidity and other kinds of impacts on the performance of these sensors?
Thank you so much, Mohsen. So let's think about this way. We are looking at the harsh environment or humans, some dangerous environment, but that's not our first application I'm looking at. So as I mentioned, we are looking at focus on biomedical application, right? So as you can guess, in remote, like hospitals nowadays, in pandemic, right? Uh, Simply speaking, we can replace the work nurses can do by this sensing robot, right? We don't need to meet nurse for first screening to get the temperature measurement or weight measurement or ECG measurement, something like that. We can do with a sensing robot. So when you think about prescriptions too, it's not common in Canada. Some area is doing that too, but we have a when you think about nurse, there's a registered nurse and then one upper level nurse who can do prescribing the medications on behalf of doctor, right? So we may generate the level of that kind of workforce by having this sensing robot, right? So that's first thing. So when something like this kind of pandemic situation, patient side also, or the nurse or the doctor side also, they don't wanna meet together. They're doing teleconference or something, but why not touching with the sensor? I mean the sensing robot, then it's gonna be huge application. Coming back to your original question, so because that area I'm looking at for future, but eventually that's gonna be useful when we send our sensing robot to battlefield, or when go to something like a radioactive contaminated area, something like that. But those applications are not really much interested at this moment because it's rare cases, right? So for the preparation of that kind of situation, of course, we need to consider all those important features like thermally resistant, right? The features, or reliable sensing features in the harsh environment, such something like that. But that is a bit outside of my consideration at this moment. Sorry. So my focus is more on how can we accept this technology in the hospital. So I'm working together with the VGH nurses nowadays to have some focus group study about acceptability of this technology. I mean, always we can develop some interesting technologies from the engineer's perspective, but if it's not ac accepted in the user level, right? The hospital level, it's useless. So initially, co-designing of technology together with the user group and the engineer is very important in that sense. So we're working together to see actually possible to get that kind of sensing robot prescription later. That's my question at this moment. Yeah.
So
Oh,
that's very very interesting. Thank you. So can you hear? So it's
yeah.
very interesting because I've been thinking about these kinds of technologies, and then when we develop new sensors or new technologies that are going to somehow replace humans, then the question that I always have is that what is the criteria for the regulatory bodies such as Health Canada or the FDA or other like health authorities in other jurisdictions about the reliability of these systems? So it's they are going to replace human to some extent, not completely. They're going to do all the measurements, but the questions are, what are we going to do about the false positive results? What are we going to do about the false negative results? And then how are they going to impact the health of the patients? I wanted to know your thoughts on these kinds of, you know, topics and these kinds of questions.
That's, I think that's a really important question. So one of the feature, whenever, I mean, Mose and Human, you guys are working on sensors too. Important feature we need to focus when we have a research in sensor field is two things, in my opinion. One is reliability, another is a sensitivity, right? So if the sensor is not reliable or sensitive enough, then it's not going to be implemented to any kinds of sectors, right? So that's one thing we want to push our limits continuously, because 3D printing, as I mentioned, initially started with the conducting materials in this talk, right? So I'm working with 3D printed sensors or 3D printed sensing robots at this moment, but I can honestly say long way to go because of the reliability issue and sensitivity issue. Sensing capability needs to be improved by any means, and reliability, of course. The reason we chose again the silver material now is I'm following just catching two rabbits now. One is printing, another thing is conducting and sensing. material which shows good quality of printability and the good quality of the conductivity is only silver now. If there's better material, then I'm going to follow that material again. So as a material scientist or engineer by training, I'm always obligated to work with that. What is better fit of material for biomedical sensing in terms of reliability and the sensitivity? So I'm still learning and still moving on to get the object.
Well, that's great. Again, I mean, this is a very nice concept, uh, which has many applications in near future even. I mean, if you look at the both Boston robotics, I think that's the where they create these, like robotic dogs and then humans that uh, they can go to different areas. I think I can imagine that this technology can be combined with those technologies, and then it has many applications in
Yes.
again for to save people's lives. That's quite interesting. So it's very nice. One other question that I have is about the choice of materials. So silver, you
Mm-hmm.
mentioned, is the main material that you're using. What are the properties? I mean, you mentioned that conductivity is something, but what are the other properties of the material that you ideally would like to have in terms of developing these kinds of sensors?
Sure. Thanks, Mojen. So basically, in order to be a sensor, to be contact with the human body, number one is safety. So the reason we use silver is we have a confidence that the silver nanoparticle almost 100% converted into silver patch, silver conductor. That's why we're using. If it is not, then it's not gonna be useful. And another thing, of course, is about. I mean, the first thing is safety. Another thing is it. Sometimes we don't use chemical sensing feature of the nanomaterial here, but if sensitivity is quite matter, then we need to consider some high surface area conductors like carbon nanotubes or graphene too, right? But we don't have that kind of requirement at this moment. But if you would like to survey or think about different printable conductors, carbon nanotube can be one of important material to choose, right?
Yeah. That's very important, because I think these sensors will be in contact with the human skin at some point, and then they should not, cause any irritation or toxicity to the human skin, which is very important, and that has to be addressed. So there are many other questions. I'm sorry, I have my question, but I want the audience to ask theirs first, and then we can always chat later. But Human, do you want to
Yeah,
take
thank you
these
so much
questions and
for
then?
this discussion. That was really great. So we have a good question from Nureddin, one of our future speaker also. He's asking about the use or the application of your sensory sensors in the diabetic patients or people with the compromised sensory function in their feet or in their hands or in the joints. Could you please explain how this can be used in this kind of situation?
Thank you for the question. So I'm thinking now. So what would be the good answer? So I haven't discussed today about the research you were working about the prosthetics. So when you think about sensing robot, eventually I'm focusing more on interaction between human and robot as a independent creature as a robot, right? But the question is about replacing or reinforce some like malfunctioning hands or some with the diabetes the patient, etc. Of course, that's the field that I'm looking at too. So in just making a part of our body replacing with the sensing robot as a prosthetic. So that's the view we're looking at. That's why I'm working more toward the sensing robot body too. So by having lightweight and mechanically tunable feature has architecture solid based the prosthetic together with the sensing applications like some pressure sensing or as I mentioned with the chemical sensing, it's going to be very fantastic, right? So we don't have any chemical sensing on hands, but someone who was a handicapped person before, but who has a superpower later with the chemical sensing, then it's going to be fantastic, right? So, yeah,
Exactly.
yeah.
Thank you. The other question from Chris, he's thanking you for excellent presentation.
Thank you.
He's interested in the hardware and software and AI aspect of the neuromorphic sensing. So, will you able to give snapshots of future research fronts of your lab in line of with these technologies?
Well, I can share with you my thought about that, the details, but I'm not the expert in AI or machine learning, so I'm working together with the expert in the computing science on that. And for the neuromorphic too, we're making the device and making the hardware, and then on top of it, collaborating with my colleagues to move forward. Thank you.
Exactly. Thank you. So, talking about materials, also Mohsen talk about different materials. You talk about carbon nanotube. Another audience is asking is, can we use gold or graphene sensors?
Of course, of course. Depends on your application. So again, gold is a bit different. Gold nanoparticle is not gonna be gold pads by sintering, but gold is good material, very reliable material if you deposit as a thin film, like a sputtering or um, evaporation, right? So those vacuum deposition can generate really reliable. I think one of the top reliable the kind of metal thin film can be made by gold. And whenever you think about biomedical or medical application, people use gold. That's why maybe the question is there. But printing is not adequate for gold. So my mandate is focusing on printing, right? That's why. I mean, if you are thinking about just using gold nanoparticles without any conversion, gold particle can be printed, of course. But if you are thinking about conductive gold, then printing is not good. You better do with the deposition. And the graphene, the question about graphene, well, graphene has really good features when it is a single layer, no doubt.
Mhm.
But if you want to make a composite with graphene with polymers and etc., conductivity issue significantly reduced. It's not going to be happen above 10 to the 2 Gm per centimeter or something, as I mentioned, right? So that's why I didn't choose. We did. I mean, we have been doing the graphene-based research in my lab too, but different applications than right. So and there are plenty of good researchers who are working on just the two-dimensional devices with graphene. That's not my field. Thank you. Yeah.
Thank you. Mohsen, we have 2-3 minutes if you have
I have
other
one more
questions.
question. So again, I mean, this is a very exciting field and very interesting research topic to me, at least. And then I'm following some of the work that Dr. Kim is doing, and then also other researchers in the field. So my question, again, that's a question that I always have. So there are two questions. The first question is about this nice robot that you showed us, the white nice robot. So how much does that cost?
Oh, good question. So 3D printing without consideration of workforce, material cost is cheap, right? I believe less than a few dollars. Yeah.
So, but that's the sense. So it doesn't add too much to the cost of the robot itself.
Hmm.
So that's very interesting. That's not. And then the other question is about the scalability of the 3D printing process. This is another question which I always had.
Mm.
And then I see that people are using this 3D printing farms these days. Uh,
Right.
what are your comments on the scalability of
Yeah.
this process?
Still, uh, I usually say still it's not possible to debate about the scalability with 3D printing. 3D printing is a niche field to have customization. I mean, very well designed for specific application, right? That is good. But in terms of mass production, I'm usually recommending to go over like injection molding or something. So first, demonstration and customizing. So why the 3D printed sensing robot is a good fit, as I mentioned. Sensing robot can be customized depending on patient and depending on the situation. It doesn't. I mean, in some sense, we can probably mass produce these sensing robots hands by having different things. But 3D printing has a good feature of the customization of design. That's why I'm pursuing this.
So another good application, thank you. But another good application is in remote areas. Maybe this
Yes.
3D printing can be used in areas that that you want to assemble the
Hmm.
entire system, on site. So I could imagine that this could be a potential application. One of my colleagues here at the University of Victoria is
Hmm.
actually developing this 3D printed hands, and then
Sounds good.
they send it to. So this is very interesting. This is very
Hmm.
interesting topic. Well, I have no more questions. Thank you very much for your very inspiring talk, Dr. Kim. I know yet you have many other commitments as an acting director. So thanks for accepting our invitation during your
Sure.
busy time, and we will chat for sure. I also would like to thank um, the participants for attending this meeting. Uh,
Thank you, everyone, participating in my talk, and thank you, Mose and Human, once again for having me today. And I really enjoyed the Q&A and the talk.
Thank you so much. Have a great day and take care.
Take care.
Bye bye.
Bye.
bye.